Right, good morning, everyone, and welcome to our session for the UKZN Mathematics Club. I see we have some good numbers this morning. So if you've joined us last week, then you know what to expect. And of course, welcome back if you're here again. So today's session is aimed at the juniors, right? So technically it's aimed at grade 8 and grade 9 students. Today's topics that will be covered will feature some content on number theory. If you were here last week, Prof. Pubalan Pillay had mentioned, he had shown you a book that he had written. And so we will also be making use of that book today for the content that we're going to be covering. So we're going to be talking about properties of natural numbers, factors, prime decomposition, a few things like that. And then around 10 o'clock today, we're going to have Prof. Ritu Parna Goswami, who's going to join us. And he will be doing something fun. He'll be talking to us about the pigeonhole principle. Now, with me this morning, I'd like to introduce you to Jaden Naidu. Jaden Naidu is a second-year student at UKZN. So, morning, Jaden. How are you?
I'm good, thanks. And you?
I'm good. So what are you looking forward to in this morning's session? Is there anything fun that you have planned for us?
I'm going to be showing you guys a really fun number theory problem.
Okay, great. And then, of course, if you were here last week, then you had met Dario Trinchero, who is a PhD student at Stellenbosch University. So if you heard last week, Dario is studying some amazing things on topological quantum field theory. So let's say hi to Dario. Hi, Dario.
Hey, everyone. Thanks for having me.
Right, so I'm going to go ahead and share my screen. Let me just spotlight a bit. Right, and let me go ahead and share. Right, so just a reminder, make use of your chat box. So whilst I may not be able to look at the chat box the entire time, we have the others who will keep track of it. So if you have any questions, please feel free to type it in there and we will do our best to be as interactive as possible. Okay, so just waiting for the screen to share. Right, it should be sharing. I see there is some type of delay. If this still happens, then what I will do is I will put my video off so that it displays a bit more seamlessly. Okay, so as I mentioned at the previous session, this is essentially the launching of the UKZN Mathematics Club, where we're doing some online sessions. And next year, you would expect to see a full program that will take place from January onwards with physical programs held at UKZN Westville campus. So please ensure that you keep updated on all of the advertisements, etc., that we would post on UKZN social media. So make sure that if you're able to, just keep track of the UKZN Facebook posts or Instagram. Just follow the official UKZN pages so that you can get more information about our mathematics club. Okay, so as I mentioned to you, today we're simply going to be talking about numbers, right? So when I talk about natural numbers, right, so then here I am simply referring to the counting numbers starting from 1, 2, 3. So these are the numbers we're working with, 1, 2, 3, 4, and so on. So these are the counting numbers. We typically denote this, if you read through the literature, as that, right? So that is how we shall denote the natural numbers. Okay, and so if I wanted to work with a set that consisted of also the negatives of these values as well as 0, so meaning I would want to include 0 with the existing list of numbers, as well as the negative values of the list that already exists in here. Right, so all of that to the left. then we refer to these as the integers, right? As you have seen in school. And we typically denote that as follows, right? So let me write that down a bit more neatly. There we go. Now, in general, when one studies this very special set of integers and its properties, right? So the study of the integers, then one is essentially dabbling with number theory, right? And that is the mathematical discipline of number theory. So that equals number theory. And this is quite a huge subdiscipline of mathematics. We have quite a few number theorists in South Africa at various universities. And one of the main areas in here is trying to understand, well, with some combinatorics, of course, is working with prime numbers. So we will eventually get to talk a bit about prime numbers. I'm sure you all know about them. And we will learn about a very nice property with regards to prime numbers today. Now, the work that I'm about to go through is a lesson from Professor Poobalin Pilay's book. So if you have not heard about it or gotten the information about it yet, we will make sure to put it up at the end of the session. You could also go to the following website. It is the South African Mathematics Foundation. So I think it's www.samf.ac.za, but we will double check this before we post. Maybe Dario or Jaden, you can just double check that it's correct. Okay, thanks, Prof. Yes, and then that's where you can get more information about this book. Right, so first off today, we're going to be talking about factors. Right, so now I'm going to need for you to use your chat box because I'll be asking you some questions and I'd like for you to be as interactive as possible, right? So let's talk about factors. So if I had to give you a number, right, and let's just say, okay, let's say I give you two numbers, right? So consider numbers A and B. Okay, so here I'm not saying anything whether it's a natural number, whether it's an integer, right? So I've just got these two numbers. We're going to end up saying a few things about it. Or maybe not yet, right? Let's just talk from intuition. So if I gave you the following number, let's just consider the number 18. Right, based on your knowledge of what you have learned in school, can you give me an example of a factor of 18? So we will formally define what a factor is, but for now, let's just quickly try to see what is an example of a factor of 18. There are some obvious ones, right? So now I'm looking at the chat box. I see nothing's come through. Okay. Right, so I see we have, right, we've got quite a few, right? So we've got quite a few come through now. So I've said consider 18 and examples, right, of factors are, as I have seen, right, quite a few responses. Thank you, everyone. So I'm just going to write down a few. I may not write down an exhaustive list, but of course we've got 1, right, we've got 3, we've got 9. Okay, good. Right, so you've written down a list of values that were all positive in nature, isn't that so? And this is, of course, based on what you've learned in school. Right, we're going to use this intuition. So you've said that 1, 3, 6, 2, 9, you've given me a nice list, are examples of factors of 18. But what about, so there are more, right? So 3 is a factor of 18. That's what I've got. So the question is minus 3 a factor of 18 as well? What do you think? Right, so now in order to explore that, one needs to understand concretely, right, what is the definition of a factor, right? So that's what I was doing below. And then I realized, let's quickly motivate it a bit, right? So we've got our numbers A and B. Okay, let's just leave it like that. Right, so we say A is a factor of B if we have that B divided by A is an integer. Okay, so look at that. Right, and I see we did have some further responses, right, afterwards. Right, so we've got, yes, you can use minus 3. Okay, wonderful. Right, so we've got a few interactive responses coming through. Right, so based on this now, okay, maybe I can have Jaden help me. Based on this definition, Jaden, can you help me just understand whether the negative values of the factors that were listed above also count as factors?
Well, when we're dividing 18 by a number, or we're dividing it by its negative, as long as our answer is an integer, we would consider that to be a factor. And because integers can be positive or negative, we would allow the negative values as well.
Exactly. Right, so we see that thus, by this definition, right, it is clear that minus 3 is also a factor of 18. So when I asked earlier, what were the factors of 18? What answers did you all give me in the chat box? This is a good observation for us to all make. You had listed the positive factors, right? So therefore, there's a very important distinction that is being made in here, right? That we had listed positive factors. So if I had asked, find the positive factors of 18, then of course you would list it as you had done. So let's consider the positive factors of 15. Now can you list the positive factors of 15 in the chat box? Well, of course, 1, right? Okay, 3, okay, 5, and 15. Okay, good. Is there anything else that we're missing? This seems exhaustive, doesn't it? Right. And so then if I asked you to find all factors of 15, then you would list this positive list, right? The list of positive factors as well as the negation of it, right? By multiplying a negative in front. So you would list 1, you would list minus 1, you would list minus 3. Okay, I should be putting it in ascending order. So you could have listed it like that. Or if you didn't want to list it, well, any order is fine, as long as we have a list of values is essentially what I'm looking for, right? And this is what you would have done, right? Or if you wanted to write it down, again, I'm just trying to point out that order does not matter. As long as you write down an exhaustive list, you could have written it down as that by simply collecting all of the values that a value as well as the negative of it, right? So a natural number and the corresponding negative value of it. So you could have just listed -3, 3, -5, 5, -15, 15. But this is just, this is not semantics, it's just listing it down. Okay, so I hope that we've made the distinction between finding factors, the positive factors, and then finding the exhaustive list of factors. Now, there's another way that one could write this down. Okay, so we could be a little bit, there are many ways that one could write down the definition of, yes,
can I just come in? I think perhaps
absolutely.
we should say exhaustive means all. You might not understand that big word.
Yes, we should. Yeah. Yes, so if I said all, or if I said exhaustive, it's the same as saying all. So there we go, right? So just some synonyms for us to keep in mind. Okay, so remember, if you've listed the positive factors, then you haven't listed all of them. That's the point that we want to make. Okay, so the next thing that I also wanted to talk about was coming back to this definition, right? So this definition was quite important to us, right? So here we had a criteria for what it meant for A to be a factor of B. And that was simply that B divided by A is an integer. Okay, so we could have also written it in a different way. We could also say, note, we could say that we can also state that A is a factor of B if, let's take a look, yeah, if B equals to n times A, right, where n is an integer. Okay, so that is another way of expressing whether some number is a factor of another number, right? And these are equivalent ways. And actually, the way in which I've written it down now is typical of what you would find in the literature, right? So it's more common to view the following criteria, right? To be able to express that B is a multiple of A, where n is some integer. Okay. Now, when I read through the first characterization of A being a factor of B, I read out this notation by saying, if we had to look here, I said that B was divided by A, right? So if B divided by A is an integer, so that was something I had said. So this leads us to talk about the following. Right? So actually what one can say is we often do this in mathematics, right? Especially when one's doing some discrete mathematics, number theory, combinatorics. Then we often write A is a factor of B as follows. A vertical line B, right? A vertical line B is another way of us writing this down, and we read this off. So this is read as A divides B. Okay, and so this is another way that you might get some exposure, or you might observe when you read the literature about factors. So A divides B. So if I have to come back here and look at the original definition, A is a factor of B if A divides B, right? Not really written out in the way that I want to say it.
Doreen, can I just interrupt you,
yes.
if you don't mind?
Yes, absolutely.
I think we should emphasize that A and B are integers in this entire discussion, not any two numbers.
Yes, they
because
are
otherwise
integers,
you'd say 3 is a factor of 3 root 2, for instance. I mean, it's not something that there's nothing wrong with that. But we rather say all the symbols in this thing are all integers because it's number theory. Unless otherwise specified.
And that point can also, yes. So I think that point can be made immediately after I had made the observation of getting out these negative values as factors. Then I can go ahead and concretely say that throughout the rest of the section, we will only consider A, B, B integers. Or would you like me to do it from
sorry,
beforehand?
Sorry.
Yeah.
Just a very quick comment as well, because it has the potential to be somewhat confusing. I know it confused me when I first saw it. There's a very important distinction here between the phrase divides and the phrase divided by, right? We have to be quite clear that saying A divides B is a statement. It can either be true or false, whereas saying A divided by B, that's an expression, right? That's A over B.
Yes.
But this is something I think that is very easy to confuse.
That is true. Okay. Thanks for pointing that one there out, Dario.
Especially because it's kind of backwards, right? If B divided by A is an integer, then A divides B. So you say it in the opposite order as well. Anyway, that's all.
Absolutely. Yeah, that's a good thing to point out. So I hope we haven't caused any confusion. And then as Prof. Pillay had pointed out, then at this point where I had introduced the definition, we would actually say consider A and B being integers, right? So we could do it from the beginning, actually. Okay, right. So here where I'm now introducing this new familiar notation, I'm only saying familiar because this is something that is going to be commonly used. It may not be familiar to you if you've seen it the first time. But now let's try to get an understanding. There's a few properties that one can consider. Okay, and in particular, right, so if I've got A divides B, then that is the same as saying that A is a factor of B, right? So that's what I've said. So in particular, 1 is always a factor of any other integer. So here I'm going to say, let me just let that go down. Okay, no, maybe not. Right, so I'm going to let B, A, B, C be elements of that. Okay, right, so now we can proceed. So 1 is always a factor of any integer. So it is true that 1 divides will always divide B, right? Similarly, any integer always divides itself. So therefore, I could always write down that B divides B. Okay, so now let's consider part C. Part C says that A divides B. So if A divides B and B divides C. So if A is a factor of B and B is a factor of C, what do you think we can conclude? Actually, this is kind of, if you have encountered this before, it's a property that's showing some transitivity. Okay, but essentially what is happening here? Dario or Jaden, would you like to comment on what property you think is going to hold true?
Yeah, certainly. So if A divides B and B divides C, then we would expect that A divides C.
Exactly, right? So we've got that happening. And then there's something special that could happen with regards to the addition as well as the difference between the integers. So if A divides B and A divides C, well, then actually it's true that A divides the sum of what it divides, as well as A would divide the difference of these integers. Okay, and then in particular, if A, okay, so here in part E, we've got A divides AB. Now, this is always true, right? So A divides a multiple of itself is always the case because A is clearly a factor of AB, right? And so these are all facts that have been listed. Of course, you could check that these two hold true if you're not yet convinced, right? So you could work through some examples. So now let's consider the following question, right? So it says determine all integers n such that 35 divided by n minus 4 is an integer, right? So how do you think one should proceed with this example? Any comments in the chat box? Find all integers n such that 35 divided by n minus 4 is an integer. Is there a quick criteria for us to work through? Right, so nothing's come through yet, I can see.
Can I answer this, Serene? I think maybe we can
Yes,
try
Prof.
some integers, 1, 2, 3, 4, and see whether it works and see if there's a pattern.
Okay. So we want to try n equals to 1. So here we're just trying something out. So let's consider n equals to 1. So if I did do this, what am I now considering? This means that I now get 35 divided by 1 minus 4, right? And so I therefore am dividing by -3. Is this an integer? Yes or no? Then let's consider n equals to 2. So we still want to figure out if that is the case, right? So I'm just waiting for some questions, for some responses in the chat box. Right, so then we're considering 35 divided by 2 minus 4, which is -2. And again, I was asking the same thing. Right, so I see that Kishalia said in the chat box that it is not an integer. Right, good. Right, and again, we're not getting out an integer, right? Okay, good. So we don't get out. So we see that -3 and minus, what property is actually emerging from here? What do you think is emerging? I'm not getting out an integer in each of these cases. And what can you attribute that to? What can you say about the relationship between the -3 at the bottom, the -2 at the bottom, and the number 35? What can we say? Can we see what's
Serene, I
happened?
think Kasharia also suggested 9 earlier.
Okay, good. Okay, let's put in 9. 35. Right, 9 minus 4 is 5. Okay. And so this is indeed an integer, right? What is 35 divided by 5? Let me just remove this. That's an integer. So what's actually happened? So my earlier question still stands. Observe. So when it was not an integer, right? What happened? What could you say was the link between this -2 and -3 with regards to 35 versus being an integer, and then we had the value of 5 in the denominator? So this was a good outcome here, right? And here, of course, this was does not contribute to us finding, or does not contribute to the list of integers that satisfy the property. Right, so what I observe here is that in particular, in order for this to be an integer, the denominator value must be a factor of 35. Do you agree that that is the observation that we can make from here? -2 and -3 are not factors of 35. However, 5 is a factor of 35. And so whenever we have a number divide 35, that number needs to be a, well, in order to get out, let me not use divides because it might confuse you, right? So in order to get out an integer, I need that the denominator needs to be a factor of 35. And that is the observation that I would like us to make. So essentially what I would like to say is that this is equivalent to saying that I need to find the integers such that n minus 4 is a factor of 35. So now it's a matter of simply listing out all of the factors of 35 and then computing the corresponding list. So what are the factors of 35? Remember, I need all factors of 35, so you need to be a bit careful. Right, we need all factors. Right, so I'm just coming back to the chat box very quickly. Okay, so I've got some responses. Right, so we've got Kashalia that's helping us out there in the chat box, and she's given us a list. Right, we've got -1, -5, -7. I'm just copying. Maybe Jaden and Dario, you can also help me by just scrolling through the chat box. Okay, so these are the values that I now have. Is this all of them?
We also had 35 coming from Caitlin.
Good.
Yashalya.
Okay. So now do we have all of them? Right, so in this list, it seems that I have 1, 2, 3, 4, 5, 6, 7, 8 values, right? There are 8 values, which are the factors of 35. But now I need to write them down in the form n minus 4. So I need to take, so these represent the n's, and now I need to compute n minus 4. So therefore, right, so find all integers such that this is an integer, and I said that's equivalent to saying n minus 4 is a.
I think you meant to say that those integers there represent the n minus 4s, and you want to find the n's, not the other way around.
Yes, yes, that's right. Yeah, so that's what I was about to come and say now, right? So these are the n minus 4s, right? And therefore, I now need to find the n's, right? So each of these represents an n minus 4. So how does one compute what n is? What should I do to each of these values? I should take each value and therefore add 4 to it. Do you see that? So maybe I could say this. No, sorry, what am I saying? Apologies, right? So what I've got here is n minus 4 equals to -1. So how do I get out what the n is? So I'm going to have to add 4 to both sides, right? So I'm only doing it for one case. So therefore, n equals to -1 plus 4. and therefore I'm getting out a value of positive 3. So you're going to do that for each particular value, right? So if I just follow the list that I've written down here, of course, the order does not matter, and I'm going to add 4 to each entry. So therefore, I'm going to get out positive 3. I'm going to get out minus 1. I'm going to get a value here of minus 3. Let me add 3 in here. I'm going to, add 4. So I'm going to get minus 31. I'm going to get 5. I'm going to get 9. I'm going to get 11. And I'm going to get 39. So are we all happy with this list in computing what the list of integers are? Right, so Mashra Gonolo, right, so let's talk about this. So n minus 4 is a factor of 35, is the equivalent statement to finding out when this quotient is an integer, right? So it says find all n whenever that quotient is an integer, right? So 35 divided by n minus 4 is an integer whenever n minus 4 is a factor of 35. That's what I've written down below. So it means that I have now simplified the question to saying, find all n whenever n minus 4 is a factor of 35. So step 1 for us was to list the factors of 35. Right, so these here are the factors of 35. Okay, and each of these values in the list are of the form n minus 4. So if I want to find n, which is what the question asks me to solve for, then I'm going to have to add 4 to every value in the list, and that is what I had done. So Mashra Gonolo, are we doing a bit better now with that explanation? Did that help? And so therefore, I have now found the list of all integers such that 35 divided by n minus 4 is going to be an integer. Okay, and that is the protocol that we will follow. Now, I was going to go through some content on multiples, but I see I am going to run out of time. So I'm going to go on and talk to you about prime numbers, right? So I'm once again going to look at the chat box, right? So let's talk about what is a prime number. Okay, so what do you understand to be a prime number? All right, so I see that Nero says prime number has only 2 factors, 1 and itself. Okay, and that's good, right? So everybody seems to be providing similar information in the chat box. Right, so let's formally just write down and summarize what it is that you have been sharing. Right, so firstly, by a prime number, we are going to only work, a prime number is going to be considered a natural number having a certain property. Right, so in particular, we're going to only work with numbers that are bigger than 1, right? So it's greater than 1. Okay, and in particular, it is a number that has exactly, right, 2 positive factors. And this is exactly what you had told me in the chat box, right? And what are those 2 positive factors? So here I'm just writing out, I'm using terminology factors in this way because we've just gone through it, right? Right, and that is 1 and itself. Okay, good. Right, so that is what we've got going on in there. Okay, so
Sareen,
we've got...
Sareen?
Yes, Prof? Yes?
Yeah, I think maybe we should say that is why we eliminate 1.
Absolutely, yes. Let me just... No, it's not working out. Right, so because we've defined it, so Prof. Pubalan Pillay has now said that we can eliminate 1 because I've said that we are considering values greater than 1, isn't that so? And so we can therefore eliminate 1 because I've said at the outset that I'm taking those values greater than 1. So thus, n equals to 1, if I considered the value 1, right? N equals to 1 is not a prime number. So we've now eliminated it out of the list of primes, right? So this is just a quick...
I'm sorry, you say it's got exactly 2 positive factors, 1 has got exactly 1 positive factor, and that is why we eliminate it.
Yes, precisely. Let me just correct that one. Right, so we're just including the reasoning again in here, right? So again, as Prof. Pubalan had pointed out, we are not including n equals to 1 as a prime number in the list because 1 has exactly one positive factor. Right, so the key thing here was 2, right? So we were looking for the value having 2 positive factors. Okay, so this is the reason for 1 being excluded and for us simply saying at the outset that we're considering values bigger than 1 because 1 is being excluded as a prime number by virtue of the definition. Okay, so can you give me an example of prime numbers, of values that satisfy the above definition? I'm just looking through at the chat box. Will 2 satisfy that definition? Does it have 2 positive factors, exactly 2 positive factors? Okay, so we've got a nice list emerging. Right, so good. Right, so I think we've understood what is going on in there, right? So we've got a nice list that has emerged. Right, so what we want to consider a bit today is we want to consider properties of prime numbers, right? And in particular, there is a property that says the following, right? It turns out that if you have a natural number, then it can be decomposed into the product of powers of primes. So that's what we will get towards, right? So we're going to have a little discussion as well, where we're going to look into this. But essentially what it says is that if you take a natural number, right? If you take a little n, then we can find, right? So then there exists prime numbers, right? P, Q, you can label them R, right, whatever the values are. And we will also find natural numbers which we're going to use lowercase a, b, c. Such that we could take this n and express it in a very specific way, right? Meaning that n can be listed as the prime to the power a multiplied to a prime to the power b times a prime to the power c, right? So it's listed in that way as a product. So it's a product of the powers of primes. Right, so in particular, if you had to take the number 120, it would be interesting to note, how could we write it down as the product of powers of primes? How can we decompose it, right? So the easiest thing to do is to firstly perhaps list it as to decompose it. So you need to have some factors, right? So you start decomposing into the product of factors. And one of the factors here, it's always easier to observe that 10 is a factor of this value. And therefore, we could write it down as 12 times 10, right? And then at each subsequent step, one could then rewrite it as a simpler. So at each step, you'd find the factors of each subsequent number. So what would be the factors of 12? And you would aim to list it such that you get out a prime decomposition, right? So you want to write it down as powers of primes, products of powers of primes. So I'd look at 12, and then I observe that I could write it down as, well, there's multiple ways to write it down, isn't that? So you could have said 2 times 6, 2 is prime. Or you could say perhaps 3 times 4, right? And so if I wanted, I will now write this down as 3 times 4 in here, because 3 is prime, and I already know that I could quickly decompose 4 into the product of 2 prime numbers, 2 times 2, right? And then I've still got the 10. So in the next step, I need to break down the 10 a bit. How could I break down the 10? So again, understanding what are the factors of 10. So perhaps here I could write it down as 2 times 5, isn't that so? So I've got 3 times 4 times 2 times 5. Okay, and then I said I wanted to break down the 4 into 2 times 2. So I can write that down as 3 times 2 times 2 times 2 times 5. And what is the last list that's emerged? Essentially, that last list where I have 3 times 2 times 2 times 2 times 5, that's a list of prime numbers, isn't that so? And here I see this is 2 to the power 3, because 2 appeared 3 times 3 times 5. And this is the prime decomposition. So here it's 3 to the power 1 and 5 to the power 1. So the prime numbers in here are 2, 3, and 5, and the powers, right? The natural numbers, the ABC, that was here, we had powers of 3, 1, 1 respectively in that order, although that does not matter in here. Okay, so I've shown you this one. So let's do the next one together. Here we've got another number.
Sareen, can I interrupt?
Yes, Prof, please go ahead.
I must apologize for interrupting you all the time. Please forgive me.
No, you should. Yeah.
All right. I think on this in the factorization, there must be some system which the learners can use to find all the factors rather than take 2 random factors. At some later stage, we can say 120 is 12 times 10, but sometimes you might see a number like 347 or something like that. You cannot see a breakage immediately. So the systematic way will be to start from the first prime number and ask, is it a factor? If it is, then you write it down as a product. And then having exhausted 2, then you say, okay, is 3 a factor? And then you look at those, whatever is left behind, and see whether 3 is a factor. So you need to know, is there any quick way of finding out whether a number, a prime number 2 or 3 or 5, whether it is a factor. So I think that is another discussion, but I'm sure our learners already know that if to recognize that 2 is a factor, the last digit must be even. And to recognize that 3 is a factor, you have to add the digits. I don't know whether they know that. And you add the digits of the number, and you see whether 3 goes exactly into the sum of the digits. And for 5, you have to just look at the last digit and see whether it's 0 or 5. So these are rules for this. I'm jumping the gun here, but the reason why I'm saying this is that you start from 2 and you see whether it's a factor, and then and you continue like that. So let's do this 3,600 in the same way.
Yes. Would you like me to list some of those divisibility properties that you mentioned, Prof, to remind them, or shall we just go on?
Yeah.
Maybe we list them.
Yeah, you can do that quickly.
Right. So we have some divisibility rules that one could use, right? And this is what Professor Pillay was mentioning. For you to observe whether, for example, the prime number 2 would be a factor. So if 2 is the last digit, then it means that that number okay, so let me just say,
You'd rather say if the last digit is even.
Yeah, if the last digit is even, then the number is divisible by 2. Okay, and of course it's important because 2 is prime. So again, so when will the number be divisible by 3? So you are divisible by 3 if the sum of the digits is divisible by 3. Okay, yes, and we can prove that, but we won't have time.
I think for the first property, it should be if the
Yeah.
last digit is even.
Did I say that?
Yes.
The last. Yes, thank you. Okay, and then let's consider 5. So you'd be divisible by 5 if the last digit would be 5 or 0, right? So the last digit is 5, and okay, for 7 we don't have a property. So maybe we can talk about, yeah, we can stop here, right? But we could talk about 11, I think. Okay, but we can stop here. So I had skipped this bit and I went on here. So we wanted to answer this question here together. Right, so we want to decompose this into its prime factors. Okay, powers of primes. Right, so how would one want to write this down? Maybe, okay, just observing that. Are there any suggestions that would come through in the chat box? Right, I see Dario has also written down, he's provided a link to trial division in the chat box, so you might want to look at that link. But I'm just now coming to the chat box to observe if there's any suggestions coming through on how we could proceed here.
I think that's
36.
36
times
times
100.
100.
Oh, sorry. Yeah, 100. Thank you. Yeah. Thank you for that. So what shall we do to the 36? Any suggestions on how I could write this one down? I see that the last digit of the 36 is even. So should I perhaps decompose that to write it, to show that this is 2 times something? Okay, Zolani, thank you for your response. Right, so I've got 2 times 18 times 100. Okay. I see 18 is still even, isn't that so? So I could further decompose that. So if I wanted, I could write that down as 2 times 9. I think you would agree there. What can I do next? So maybe let's break down the 100, right? So again, I see that 100 is also even. So I could write that down as 2 times. Okay, I'm just going to keep that bracket there for now, but it doesn't matter, right? And then this would be 2 times 50. So now what I have happening is that it is equal to 2 times 2 times 2 times 9 times 50, right? Which is 2 cubed times 9. But what is 9? How can I express 9? Would you agree that I can write down 9 as 3 times 3, which is 3 squared? And then 50, it's even. So can I decompose that a bit further? Yes, I can write that down as 2 times 25. Okay. So now 25 is no longer even. So what else can I do? But I noticed that 25 is divisible by 5, isn't that so? So here I'm just going to write this as 2 to the power 4. I've collected the other factor of 2. And I observe that 25, since it is divisible by 5, is just 5 times 5, which is 5 squared. And so this is the prime decomposition here of the number 3,600. Now, I did plan a lot more for us to talk about, but it is 10 o'clock. So what I'd like to do is perhaps give an opportunity to Jaden and Dario, who had prepared some examples. Now, Jaden, in order for you to talk about your example, you're going to need to present a specific result. Do you have that result with you, or for you to quickly mention it and then go through your question?
Yeah, I do have it written down in one of the slides.
Okay, perfect. So maybe okay, so what Jaden is going to end up doing is we're going to talk about how does one count factors, right? So how many factors? So we know how to decompose any number. We could write down any number as the product of prime powers, but the question is one able to count the number of distinct factors in that decomposition when we write down that product? And that is one of the key questions that arises next, meaning if I give you a natural number, then how many distinct, meaning how many different factors does it have? So in particular, if we looked at the above example, where N2 equals 3,600, we saw that this is just 2 to the power 4 times 3 squared times 5. How many distinct factors do we have in here? right? So there's actually a really nice result that Jaden will tell you about as he answers the question that he has prepared, right? And Jaden, maybe when you're demonstrating your result, you could use this particular example where we had 2 to the power of 4, 3 squared, and 5 squared as the prime decomposition for 3,600.
I do have another one on the slides, another
Okay,
number.
so you use your example and then I can wrap it up with this one. Perfect. Right, so I'll stop
Okay.
sharing and I'll give you an opportunity.
Okay. So let me just share my screen. Cool. Can you guys see that?
Yes.
Okay, so I'm going to look at, it's the same problem, but we're just going to look at the number 180, and we're going to try to figure out how many factors that number has. So what we're going to do is we're going to use this result that the reason why we have to know how to prime factorize numbers is so we can use this result over here. So the result says if n is given by this prime decomposition, and these variables, they're just variables, so it doesn't matter what they are, they're just prime numbers, and then we raise them to some exponents. So if we have n written in this form, then we have a formula for how many factors that n has. And we can prove this, but we don't have time, so I'm just going to show you the formula and then how to use it. So here we want to find the number of factors of 180. So in this case, n should be 180. And our result says that if n is written in this p1 to the a1, etc., that form, then we can figure out how many factors it has. So our first step has got to be to actually prime factorize 180. And so we're going to do the exact same thing. We're going to try to pull out a factor. And the first factor you might notice is 2 because 180 is even. So we're going to get 180 is 2 by 90. So when you divide 180 by 2, you get 90 out. And then because 2 is prime, we're just going to repeat that, starting with 90. So we're going to try to factorize 90. And we can do that by 2 again, times 45. And now we have to factorize 45. So we see that 45 is not even, so we can't pull out a 2. But what you might notice is that the last digit of 45 is a 5, so we can take out a 5. And if we do that, we get 45 is 5 times 9. And then the last step would be to factorize 9, because 2, 2, and 5 are all prime, so we just have that 9 to work with. And then 9 is 3 squared, you can pull out a 3, and then that's your final factorization. So at the end, we got that 180 was 2 by 2 by 3 by 3 by 5. So we're almost done with this, but remember the form we need it in is when we have powers, we have primes to powers, but we don't have the powers here. We just have copies of 2 and copies of 3. So we just need to make a slight modification to it because we want it in this form over here. And we can just say, okay, 2 times 2, that's 2 squared. 3 times 3, that's 3 squared. And 5, well, that's just 5 to the 1, right? So now we have the bases, so the 2, 3, and 5, now those bases are all different. So we actually do have it in this form that we wanted, where we have P1, which is some prime to a power, times another prime, which is 3 to a power, times a third prime, which is 5 to some power. So to write it down explicitly here, we have P1, which is our first prime, is 2. P2 is our second prime, and that's 3. And then P3 is our third prime, and that's 5. And then our exponents are 2, 2, and 1. And now that's exactly what we needed for that result that I showed you at the start. We have written 180 in this form. So now we can just apply this formula which we have, and that will be the number of factors. We'll be done. So we have A is 2, B is 2, and C is 1. So the number of factors will be A plus 1, which is 2 plus 1, times B plus 1, which is also 2 plus 1, times C plus 1, which is 1 plus 1. So we get 3 times 2, and that gives us a final answer of 18 factors for 180. And what's important about this is if we hadn't used this formula, then we would likely have had to try every number until we figured out which ones were factors and which ones weren't factors. So we would have had to try every number smaller than 180. And that would have taken a long time. And we would have had to find all those factors manually. But because all we were interested in was finding the number of factors, we could just use that formula without actually having to find the factors, which would have taken a lot longer. And yeah, that's about it.
Thanks,
Are there
Jaden. That
any
was wonderfully
questions?
explained. Yeah. Seems like we don't have anything coming through from the chat box. So I think that was very well done. Thank you for sharing that example.
Okay.
So we have gone a bit over time on our session. Daria, I just want to quickly check if you have any comments or last things to add.
No, I think that was excellently presented. Thanks, Jen.
Cool.
Okay, and so what I'm going to do now is I'm now going to quickly hand over to Professor Rituparna Goswami. And as I told you at the beginning of the session, Prof. Goswami is going to be talking to us about something really interesting, and that is the pigeonhole principle. So I'll quickly hand over to him. Yeah.
Thank you very much, Sirin, and everybody else here. I hope I am visible and audible as well. And you can see the whiteboard behind me.
Yes, we
Perhaps
can.
I am the oldest one in this whole group because still I love the old blackboard, board and chalk kind of a thing rather than making slides. So today I decided to talk about something very simple. Because whenever you talk about maths, people say, oh my God, it's numbers and algebra and A, B, C, etc. And oops, it's not for me. This is just to show you that a simple common sense, which even a toddler has, can solve so amazing number of mathematical problems you can ever think of in different fields altogether. So let me start with, let's draw something. Can you see? Okay, that's one pigeon. That's another pigeon. So in a way, you have some pigeons with you. And not only pigeons, you have some holes where you can hold a pigeon and put them in. Just like in olden days when people used to have pet pigeons and they used pigeons to send informations. In fact, when I first came to South Africa, there was a competition that one has to send a 1 GB file from UCT to Stellenbosch, and which one is faster if you just tie that 1 GB thing in a pigeon's leg and let it fly, or you use the internet at that time. I'm talking about 2007. Of course, the pigeon was faster than the internet at that time. So anyway, so we have some pigeons and some holes, okay? And these holes are big enough so you can put as many pigeons inside the hole as you like. That's not a problem. Then in mathematics, there is, we call it a principle that let the number of pigeons be P, number of holes be H. And I say that if the number of pigeons is more than number of holes, that means P is greater than H, then there exists, I'm sorry, whenever you write E in this opposite way, in maths it means there exists one hole with more than one pigeons.
Excuse me, Prof. To briefly interrupt you, maybe we should say at least one hole with more than one pigeon, right? There could be more than one hole.
Yes, so I'm saying there exists one hole.
Yes, I agree.
Yeah,
I just to be perfectly clear, yes.
Yeah. So with more than one pigeons. Now come on, I mean, isn't it crazy to call it a principle, mathematical principle? Even a toddler knows that when the mom says, go and keep away your toys immediately. I want the room neat. And the toddler knows if his number of toys is more than his number of boxes, then of course one box will have more than one toy. I mean, it's such a common sense. But believe me, this simple common sense can actually go quite far. In fact, mathematicians always love to generalize stuffs. So this can be, with the simple common sense, can be generalized to a little bit more, that if the number of pigeons is greater than some multiple, just now you heard about multiples and factors, some multiples of number of holes, then there exists one hole with number of pigeons greater than that multiple. So this is a bit generalization of the first blue line, what I wrote. Nothing more, nothing less. So you must be wondering, this is such a simple thing, and how can we really use that to solve hardcore problems? To go there, let me go step by step. Let me see if we can solve some day-to-day problems, especially in our current situation in South Africa, using this so-called hardcore mathematical principle, which is nothing but a toddler common sense. Suppose you want to pack your bags for the next day's school, and it's 7 in the evening, everything is dark, and suddenly, 8 in the evening, and ESCOM says stage 2 starts, and poof, all lights goes off. Now you know in which drawer your socks are there, school socks. And also you know that in every school there are two kinds of socks, one which you wear for sports days, and one which you wear for the usual days. Suppose one is blue and the other is black, suppose. Now in that pitch dark situation where you don't have candles or torch, you want to find one pair of socks with the same color. But as you can see, as you cannot see rather in the dark, it's very hard to differentiate between black and blue. So what do I do? But I need at least one pair of socks of the same color. I cannot wear one blue sock and one black sock and go to school the next day. So, coming back to the pigeonhole principle, we have ample number of blue socks. Sorry, I wrote it with black, but that doesn't matter. Okay, let me change it to blue. So we have some number of blue socks in the cupboard and some number of black socks. Okay? So I start picking one after another. The first sock can be blue or black, I don't know. The second one can also be blue or black, I don't know. I mean, if I just take two, it can be two blues or two blacks or one blue, one black. So how can I be 100% sure that I'll have two socks of same color? So I'll pick one more sock. So now I have three socks and two holes. One is blue and one is black. So by the pigeonhole principle, we know since the number of socks are more than number of holes, there will be one hole with more than one sock, or rather two socks. So just by picking three, I can be 100% sure. That is the most important thing. In pigeonhole principle, we are not talking about probability or chances. Okay, the chance of getting two is 2/3 or something. Nothing like that. I want to be 100% sure that I'll have two socks of same color. So what do? I just pick three socks. And I am assured that either I'll get two blue socks or two black socks. I'm done. And of course, we can generalize it a bit more from here. Say we want now not one pair of socks, but two pair of socks of same color. Rather, four socks of same color. So how many of them I have to take by this generalized one? Suppose I pick 7 socks. Then I am assured, 100% assured, that there will be either 4 blue socks or 4 black socks. And of course, if you want, say, n pairs of socks of same color, first one was 3, now it's 7, you can immediately see that it is 4n minus 1 socks you have to pull out one after another to be 100% assured that these socks are of same color. So it's one very, day-to-day necessity which can be happily solved by this pigeonhole principle. Let me come to a very funny, scenario now. If I ask you a question, in the whole eThekwini municipality area in Durban, the whole greater Durban, as you call it, how many people are there who are non-bald and non-shaved headed, completely shaved headed, who has exactly the same number of hairs? Now you must be thinking I'm mad. First of all, I want to count the number of hairs of people, which is absolute madness, and then to assert that whether there are 2 peoples or more than 2 people with exactly the same number of hairs. That's crazy, isn't it? Well, if you just do your Google search, you will see it's not such a crazy question. It's a very interesting question. If you are not absolutely, completely bald, like Professor Pillai is slowly going to be at some point, his hair is going down quite fast. But jokes apart, anyway, a person, more or less, a grown-up person, has a maximum of 300,000 to 400,000 hairs. You can estimate that, basically. Take a 1 centimeter square area on your skull, cut the hair. you will see the order is around 100 there, and then, I mean, order is around 1000 there rather, and then do the whole maths. It's quite simple. You can estimate that any grown-up person with hair, the average amount of hair on a person's head is around 300,000 to 400,000. Let me be absolutely very generous and say, let the maximum number of hair on a person's head is 500,000. A person who is non-bald and non-shaved headed, the maximum number of hair on somebody's head is 500,000. Perfect. Now, so let me write down maximum number of hairs in somebody's head cannot cross 500,000. Okay? And what is the population of the eThekwini municipality area? Again, go back to Google. It's just one search. So in 2023, it was found that it's around number of persons in Greater Durban is around 3.28 millions. Millions means 10 to the power 6. So of course you see the number of person is much more than the number of possible hairs on their head. So if I do a 500,000 pigeonholes like this and bring each person. Okay, so your number of hair is say 300,128. So I put him in that hole and continue with it. But you see the number of persons is much more than number of holes. Even if we think that, okay, the total number of completely shaved-headed or bald people in Greater Durban area is around 5% of the population, which comes down to 3.28, 5% would be around 164,000. So you subtract 164,000, still it is greater than 3 million. So you divide 3 million by 500,000, what you get? 6. So that means there must be one hole which represents the number of hairs with more than 6 people. In other words, there is at least 7 people in the whole Greater Durban area with exactly the same number of hairs. Now, don't start pulling your hairs after this. And what did I do to come to this conclusion, this definite conclusion? Am I a soothsayer? No. Did I go to all the barber shop in Durban and started counting hairs? No. I just sat on my table and used this simple common sense to come to a perfectly mathematically true conclusion that there is at least 7, if not more, people in the Greater Durban area with exactly the same number of hairs. Okay, let me give you another fun example regarding tonight's match. Now, don't worry, I cannot say any definite thing about the results of tonight's rugby match. Like any one of you, I am keeping my fingers crossed with my full support towards the Bockies. But I can say some very interesting thing about the match in an absolutely definite way. So the match is going to take place in a stadium called Stade de France, which is the national stadium of France in Paris. Okay? Whose total capacity is 800,000 people. I'm sorry, 80,000 people. So 80,000 spectators can watch the match sitting in the ground tonight. And as far as I can see from the internet, all the tickets are being sold. So we can be rest assured that 80,000 people will be sitting there, either cheering for England or cheering for Bocky, that's different, but there will be 80,000. Good. Now let me do something. Let me divide 80,000 by 366. I'll tell you why I'm doing that. And by the way, I'm sorry, as I said, I'm a very old person who don't know how to use calculators. So I use this old style of division. So you can immediately see that 366 goes twice, and that will be 732. So there will be 68, 680. 366 will go once here, so 366.
Prof, can you move your camera a bit?
Oh, sorry.
Thank
Is it
you.
okay now? Yeah.
Yes.
So 366. So this is 453, 334, and 366 will go 8 times. 48, 4, 48, 52, 5, it's 20. Oh, sorry, it will go how many? 3340. 1 0 is left. So it will go 8 times. So 4, 2, 29. Yeah. And the remainder will be something less than 366. So if we divide these 80,000 people by 366, we'll get something more than 280. Now, why did I divide with 366? This is the maximum number of days possible in a year. In general, it is 365, but you know on leap years, February has 1 extra day, so it is 366. Now, if these days in the year are wholes, and we put each of these 80,000 people in those holes according to their birthdays, then I am rest assured that there are at least 219 people today who are watching the match at Stade de France will share the same birthday. Not only that, in one day there are 24 hours, right? So let me divide 219 by 24. We'll get a little, so suppose I divide 219 by 24, we'll get something little more than 9. So among these 219 people, there will be 9 people who doesn't only share the same birthday, but also the same birth hour. So suppose they were born in, say, 21st of October, and one of them has born between 7 in the morning to 8 in the morning, there will be at least 9 people, sorry, at least 10 people rather, who will share the same birth hour. Crazy, isn't it? I mean, just imagine I don't know these 80,000 people at all. I have never seen them, I have never met them, never heard about them. But just by using the simple logic, we can say so definite things about these people. It's absolutely crazy how powerful this method can be. So having done with these fun examples, I mean, of course, they are not fun, as you can see. You can come up with such definitive statement. And by the way, this is more important. I'm not talking about any chance or probability that, okay, there is a 60% chance of today it will rain or today it will be sunny, kind of that, which never happens though. I mean, whenever you get the weather report, you always inverse it to get the right weather. Here, I am not talking about any chance or any percentage. I am saying it will happen. There will be 219 people sitting in that stadium today who has the same birthday. Well, so now how can we use this principle to solve some Olympiad type problems? Say, you are all here to know how to solve those kind of problems, which you get. I mean, there are lots of Olympiad type question papers in the internet. And so let's see, one such question is, perhaps all of you know the game of Scrabble. So in a bag, I have kept the cubes, I mean, all the alphabets cut together separately. How many alphabets are there in English language? We all know there are 26 alphabets. And everybody of you is arbitrarily picking alphabets one after the another and writing it down on a straight line. Okay. So say somebody start with P and then R and then A and then C and goes on. Some other starts with B and Q and Z and E and goes on and like that. Now, what I am claiming is that no matter which way you write those alphabets, in which order you write those 26 alphabets, there will be always 4 consecutive consonants. It's a big claim, isn't it? First and foremost, there are how many ways to permute those 26 alphabets? I'm not going into the proof, but the number of permutation is in the first place. You can put any of those 26. In the second place, since you have already put 1, you can put any of the 25 left. In the third place, you can put any of the 24 left and goes on till 1. So this is called a factorial function and denoted by the number with the exclamation sign. And as you can see, it's a huge number. So these are the total number of permutations all letters of English alphabet can have. It is a huge number. Now, if I just sit there and go on checking, oh, whether this has 4 consecutive consonant, or the second one has 4 consecutive consonant, I won't be able to finish it in my lifetime. As simple as that. But then, how am I so assured that whatever permutation from these huge number I take, every one of them will have 4 consecutive consonants? Can't help. So let's see how to go about it. Since we are talking about 4 numbers in a row together, and we have 26 alphabets, let's divide these 26 alphabets in the sets of 4. So in the first set, we have 1, 2, 3, 4. Whatever they may be, vowel or consonant, I don't care. In the second set, 1, 2, 3, 4. Third set, 1, 2, 3, 4. Fourth, 1, 2, 3, 4. Fifth, again 1, 2, 3, 4. Sixth, 1, 2, 3, 4. Am I done? No. It's 4 times 6 is 24. 2 more left. So in the last set, I'll have only 2. Now let's think just like those simple common sense toddler logic. If we don't want 4 consecutive consonants, we must stop that flow by inserting a vowel. Right? Now, how many vowels are there in English alphabet? There are only 5. So you have to insert 5 vowels in these 6 holes. That means one of the hole has to remain empty. Whatever you do, whichever hole you plug in a vowel, one of them has to remain empty. I mean, without vowel. So that hole will necessarily have 4 consonants consecutive. Interesting, isn't it? I mean, even without checking the whole sequence of alphabets, just by thinking it in, rather thinking in the box rather than out of the box, how many vowels we can put in these 6 boxes, we can immediately see that there will be one box, whichever it may be, without any vowel. We don't have enough vowels for that. So since this one box will only have consonants, therefore, in whatever sequence I write my English alphabets, there always will be 4 consecutive consonants. Okay. So this was a problem regarding combinatorics. That is a part of mathematics where we deal with combination of different objects and how we arrange the objects together, so on and so forth. And you might think, okay, pigeonhole principle is all about arranging pigeons inside the hole. So it's just a principle for these kind of problems. I'm sorry, no. Let me come up with a problem from geometry. In the last week, Professor Pillai gave you a very nice idea of geometry. Now let me give you a question from geometry. Let me have a square of side length A. A can be anything, any real number. I don't care. So this is A, B, C, D. It's a square of side length A. All the sides have equal length and all the angles are 90 degrees. No, it's a square. And I want to put 10 points inside the square. Wherever I put, that doesn't matter. 10 arbitrary points inside this square. Okay? Say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now I call one of you, put 10 points, whatever you like. You put 10 different points, absolutely. There are infinite points in this square. Wherever I want to put the points, I can put. Now what I am saying is, it doesn't matter whatever way I put my points inside this square, there will be always 2 points whose distance between them, say D, will be less than or equal to root 2a by 3. Crazy, isn't it? I put my own points, you put your own points, Sirin put her own points. Everybody in this world puts their own points. We don't have any aliens till now. If we had aliens, they will put their own points. It doesn't matter. But whatever point we put, there will be always 2 points. The distance between those two will be less than or equal to root 2a by 3. Can we prove this? This is such a definitive result. Well, let's see how we can prove this. So what I'll do is, I'll cut this square in 9 equal small squares. Okay? 1, 2, 3, 4, 5, 6, 7, 8, 9. And within a square, by the way, what is the maximum distance between 2 points possible? Suppose I have a square like this. What is the maximum distance between 2 points possible if I want to put the points inside or on the square? Of course, by inspection, you can see this is the maximum distance, right? If we put it along the end point of the diagonal. Because diagonal inside a square is the maximum length line. There is no line inside the square that can beat the diagonal. And for a square of length A, what is the length of the diagonal? Root 2A. How do I know this? Simple Pythagoras theorem. A square plus A square under root is root 2A. So inside a square, we can have 2 points at a maximum distance of root 2A, and that's all. Okay, now coming back to our original square. Now in this square, I have to put 10 points. How many holes are there? There are 9 holes. So in 9 holes, we are putting 10 points. That means there will be 1 hole with more than 1 point. That is obvious. So there will be 2 points, say, in this hole. And what is the maximum distance of these 2 points within this hole is possible? It is root 2 times the side length of this small square, which is A by 3. Because I have divided this side lengths in 3 equal parts. So therefore, the distance between these two will definitely be less than or equal to root 2A by 3. I mean, now perhaps you are getting the feeling that how powerful that toddler common sense is. That it is not only in combinatorics or things like that, we can say definite things about things we have no idea about how to proceed. There can be 10 points in absolutely arbitrary manner, but still this result will always be true. Okay. Another very, very interesting problem, and this type of problems do come in this Olympiad type examinations. Nowadays, especially after COVID, we all do meetings in Zoom, right? And especially, I mean, if you work in some business or office, you have to do n number of meetings every day. So suppose 6 people are meeting inside a Zoom. 6 persons. Okay? Having a Zoom meeting. Now, whoever these 6 persons is from the whole world, I can choose any 6 person, I don't care. There will be always either one scenario where 3 persons knows each other, either this will be true or 3 persons don't know each other. So whichever 3% you bring from the whole world, from whatever country, I don't care. Bring them from North Korea, bring them from Guatemala, bring them from Hawaii, bring them from Kamchatka, I don't care. Either this will be true for this meeting of 6% or this will be true. That 3 persons will know each other or 3 persons who don't. Again, such a definitive statement. So let's see if we can make some head or tail out of it using our pigeons and holes. So let this be one of the person. Let this be me. Okay? So there are 5 more persons in the room. 1, 2, 3, 4, 5. Let's call them A, B, C, D, E. Okay? Now with each person, there is 2 possibilities regarding myself. I'm talking about me. Either I know A or I don't know A. Either I know B or I don't know B. Either I know C or I don't know C. Now if we make 2 holes, one hole with no and one hole with don't know, for me, I'm talking about me. Then by pigeonhole principle, there are 5 people to be put into either this hole or that hole. So one of the hole will have more than 2 people. So either I know 3 people or I don't know 3. That will always be true. So let me take the first case that I know 3 people. And I put a blue line for me knowing these people. So suppose I know 3 people, C, D, and E. But if I know 3 people, that doesn't mean these people know each other. I have many friends who are not common friends with, who are not friends with them. They don't even know each other. So this doesn't say anything else. But now look carefully. We are looking for either a triangle of 3 people that know each other or a triangle, say red triangle, for 3 people who don't know each other. So look carefully, if any one of them knows each other, suppose, say C knows D or D knows E or E knows C, then the triangle is complete. We have a blue triangle, so 3 persons know each other. But then this is not guaranteed, right? If this is not guaranteed, then there will be, suppose none of these 3 persons know each other. Then they don't know each other. Let me put a red line for that. So I completed a red triangle, which is my point 2. So if at least one of them knows each other, it is point 1. And if none of them knows each other, it's point 2. So it's like head I win, tail you lose. We'll always have either a blue triangle or a red triangle. This is for the no part. In an absolute similar way, I can start with the don't know part with 3 red lines and say that either the red triangle will be complete or a blue triangle will be. And we are done. So now you can see that these complicated kind of questions, which makes you just sit back and think, oh my God, how do I do it? Is so easy with the pigeonhole principle. I'm coming to the end of my time, so I'll finish it with a very important kind of problems which comes in many variants in all these tests and exams, which is called 3-color problems. Now, what are the 3 colors? suppose the three colors are red, green, and blue. And I put one color on each point of this whiteboard. Okay. So each point of this whiteboard is either colored with red or green or blue. I can have a monochromatic board, fully colored red or blue. I can have a dichromatic board, half of it color red, half of it color blue. It doesn't matter. Whatever way you want to color this board, it's fine with me. As far that all points are colored with either red, green, or blue. Okay. Now I give you a distance d, which is smaller than the dimensions of the board. Any distance, any real number. I claim that there will be always 2 points separated this d distance apart, which have the same color. Whatever way you colored the board possible. You can draw pictures, you can draw flowers, you can draw anything. But there will, and I give you a distance d, I can always find 2 points with the same color, distance d apart. I mean, think about the problem, try to digest the problem. Crazy, isn't it? It's absolutely crazy. I mean, there is no way to even, how do I proceed with this? Because I can color the board in any way I like. And there are infinite points on the board. So let's see how to construct a solution like this. So take any point, say A, which is colored red. Okay? And try to locate another point which is root 3d apart with a different color. Now you will say, how are you sure that this is possible? Of course, I am not sure. This point can also be red. And if I cannot find any point of different color at a distance of root 3d from this original point, that means I can construct a circle of red with this radius. And then from that circle, I can immediately cut out a chord which is of a distance d, because this is the radius. I can always cut out a chord which is smaller than the radius, which is both red, and I am done. I found 2 points which are red. Simple. So if we don't find any other color at a distance root 3d, the thing is simple. But what happens if I find another color? Say I find a blue color here. Okay? So here I have a red color point, here I have a blue color point at a distance root 3 by 2d. Now what do? I'll do a very interesting construction. Maybe some of you who are doing geometry will know how to bisect a line using perpendicular bisector with your compass. So put a compass like this, draw one arc, another compass, and you construct a perpendicular bisector of this line. Okay? And on this perpendicular bisector, cut 2 points at a distance d by 2 from the center. So this point is at a distance d by 2 from here. This point is at a distance d by 2 from here. Now, why am I doing this construction? Very simple. So now this half distance will be root 3 by 2d, and this half distance will be root 3 by 2d. Now let's join this point and this point. What is the distance between this point and this point? This square plus this square under root, which is d. Again, this by Pythagoras theorem is d. And also these two similarly will be d and d. So in other words, I constructed a very nice looking rhombus with each side length d, whose one side is red, one point here is red, the other point here is blue. Now I have 3 colors and 2 points to fill. If I fill it with either red or blue, then I am done. Because if I fill it with red, then I found 2 red points at a distance d apart. If I fill it with blue instead, again I found 2 blue points at a distance d apart. Hang on, you will immediately come to me and say, you forgot there is a third color called green. I agree. Do I have a green thingy here? Yes, I do. So you will say, okay, let me be very intelligent. I won't put red or blue in both of these points. I'll put green. So here is a green, here is a green. But my dear, you forgot we constructed a rhombus. This is d by 2, this is d by 2. So these 2 greens are now d distance apart. So it's a classic example of heads I win, tail you lose. You have all played tic-tac-toe and you know how to come to those points where wherever you put your thing, you are going to lose. So this is something like this. So this is a very interesting 3-color problem. There are many problems like this, 3 colors on a plane, 2 colors on a line, and these can be solved using this so-called childlike pigeonhole principle. So it's 11:02. I stop here. Any questions? Sirin, can you see the chat? And
there are none that have come through so far. Whatever questions did come through, we answered them in the chat.
okay.
Yeah.
Fine.
Yeah, it was a very interesting session, Prof. Thank you so much for that. And it really held everyone's attention as well, because you kept it so lighthearted. So thank you for using the real world problems. I think
Pleasure.
many students found it enjoyable. Yeah.
It's very unfortunate that
So
by
we
pigeonhole
shall bring
principle, we
this
cannot
session to a
definitely say
close.
that South Africa will win today. But yeah, come on, Bockies. That's all. Thank you so much.
Indeed. Thank you, Prof. I want to take the opportunity to thank Professor Rituparna Goswami. I want to thank Dario Trinchero, as well as Jaden Naidu. I see that my internet connection is still unstable, so I'm going to still keep my video off. I hope you can hear me. Can you confirm that you can hear me?
Yeah, we can.
Okay, good, because I keep on getting notifications. But yes, so thank you to Dario, thank you to Jaden, thank you to Prof. Goswami for making the session possible, and more importantly, thank you to the students. As usual, we will compile the notes from the session today and we will have it emailed to you. The recording of the session will appear on the NITEX YouTube channel.